Hi, welcome to the final lecture of MATH336. This is on section 5.2, the method of elimination. So we're talking about systems of differential equations now. Last section we saw how we can take a differential equation that is second order or higher, or even a system of differential equations with that are second order or higher, and we can rewrite it as a system of differential equations that is first order. And we talked about how this is important because then it allows us to take basically any type of differential equation and write it in the standard form that is required in order to solve it numerically on a computer. Now, for large systems of differential equations that arise in practice, in order to solve these types of problems, we really require numerical methods and also numerical linear algebra. So at some point, you may learn about how the solution of these systems of differential equations, if it's linear with constant coefficients, then this comes down to solving an eigenvalue problem in numerical linear algebra. However, if the system is small enough, we can actually solve it by hand, and we can use the method of elimination to solve it. So I'll show you how to use this method of elimination to solve a small system of differential equations. And yeah, it's pretty straightforward. So it's just a matter of taking the system of differential equations and then kind of doing the opposite of what we were doing last time, where we want to identify the higher order differential equation, which we then solve that. So we're going from the system, first order system of differential equations to a single differential equation that has that is of a higher order. Okay, so let's have a look at this example. So here we have a system of differential equations. X involves x and y, and they're both, the derivatives are with respect to time. And we can see that the method that we were using last time in 5.1 isn't so easy to do here. Last time we just took like the derivative of one of these equations and then substituted it into the other equation. But that's not really going to work so nicely. What we need to do here is solve one of these equations for either x or y, and then substitute it into the other one. So for example, this first equation here, it has two x's here and just one y. So we can solve this first equation for y, and then we can substitute that into the second equation. So whatever we get for y here, we'll substitute it in here. And then also we'll take the derivative of y and we'll substitute that formula here. And then this will become only x's. So you'll only have x's here and only x's here, so there won't be any y's left anymore. And then we'll get a differential equation for x. You could also go the other direction as well. You could start with this equation here and solve it for x, and then substitute that back into here and here. And then this equation will become a differential equation just in y. And then we can solve that using techniques that we've learned in this class. Okay, so let's do the first one. So let's say we'll solve the first equation for y. Okay, so, and remember, we could solve the second equation for x. So that's another option, but we'll just do it this way. So we'll solve the first equation for y. So what do we get? We're going to get y is equal to 1/2 x prime plus 3x. Okay, and we're also going to need the derivative of y. So the derivative of y is going to be 1/2 x double prime plus 3x prime. Okay, and now we substitute into the second equation. Okay, and what do we get? So it's going to be y prime. So maybe I'll just write the second equation down again. Y prime is equal to minus 3x plus 4y. Okay, now we'll do our substitution. So y prime is 1/2 x double prime plus 3x prime is equal to minus 3x plus 4 times 1/2 x prime plus 3x. You see now we have just a single equation that is in terms of x. There's no y anymore. Okay, so let's simplify this. So I'll multiply both sides by 2. Like that. So I multiplied both sides by 2 and I distributed this 4 across this. And then I'm going to move everything to the left-hand side. So I'm going to have 3x minus 4x, so that's minus x prime. 3x prime minus 4x prime. So minus x prime. And then on this side we have plus 6x, so that'll become minus 6x, like that. Okay. Now we do have a choice here how we want to solve this equation. We can either solve it in terms of, we can use the chapter 2 methods, or we can solve this equation using Laplace transforms. And in order to do either method, we do need, so we have these initial conditions that we need to use in order to solve it. So we have the initial condition x of 0 is equal to 0, but this y of 0 equals 2, we need to use that to get a second initial condition, because to solve a second order differential equation like this, we do need a second condition here. So let's see, what is y equal to? Y is equal to this. So let me just put this here. Y of 0, maybe I'll make it like this. So y of 0 is equal to 1/2 x prime of 0 plus 3x of 0. Okay, let me just put a divider here. So therefore we get 2 is equal to 1/2 x prime of 0 plus 3 times 0. So let's make a little bit more room here. And so therefore x prime of 0 is equal to what? So this is 0, so that goes away. So 2 times 2 is 4, so it's equal to 4. Okay. All right. Oh, I guess actually now that I think of it, another easy way to do that would be to use this equation here. So let's try that as well. So let's do this x prime equals this stuff. So let's try that as well. So let's see, what do we have? Copy that. And let's make it blue. And then let's write down the initial conditions that we have. Right? Y of 0 is 2. Yeah. And so therefore, x prime of 0 is equal to negative 3x of 0 plus 2y of 0, which is negative 3 times 0 plus 2 times 2, which is 4. So that actually was a little bit easier to do. So let's use that. So x prime of 0 is equal to 4. Okay. Well, we might as well use, well, I don't know. I guess maybe we do need more practice with the chapter 2 techniques, just to remind ourselves how the chapter 2 techniques work. So let's try that. So using the characteristic equation, we get r squared minus r minus 6 equals 0, and we factor it. And so r is equal to 3 or minus 2. And so therefore the complementary solution, or in fact it's because it's homogeneous, it's just the entire solution is going to be the following. It'll be C1 e to the 3t plus C2 e to the negative 2t. Okay, and now we want to determine the C1 and the C2. So we take the derivative, and now we're going to substitute our conditions in. So x of 0 equals 0. We'll do that one first. And this tells us that 0 is equal to C1 plus C2. And then x prime of 0 equals 4. This tells us that 4 is equal to 3C1 minus 2C2. Okay, so now we have this linear system that we need to solve for C1 and C2. It's just a 2 by 2 linear system. So let's use Cramer's rule in order to solve it. So Cramer's rule says that C1 is equal to, so what's the matrix first of all? So it's 1, 3, 1, minus 2. So that's the determinant on the bottom. And on the top, we replace the first column with the right-hand side, 0, 4, and then 1 minus 2. And we get negative 4, so it's 0 minus 4, so negative 4. And then we have negative 2 minus 3, so it's negative 5. So we get 4 over 5. So quick and easy. So now we'll do C2. So C2 is the same, but instead of replacing the first column, now we replace the second column with the right-hand side. Okay, so that's the important thing there, is where that right-hand side goes. And what do we get? So we know the bottom is minus 5 because that doesn't change. On the top we get 4 minus 0, so it's 4. So we get minus 4 over 5. And so therefore x of t is equal to 4 over 5 e to the 3t minus 4 over 5 e to the negative 2t. So there's our solution for x. Now let's determine our solution for y. So what is the formula for y that we have? So our formula for y is this one here. So let's calculate y. So let's see, let's put this over here for a second. So I'll say since y is equal to this, we have y of t is equal to 1/2. And now we're going to put x prime in here. I guess I'll just calculate x prime again using the 4/5 that we have here. So this will be, let's see, 12 over 5 e to the 3t minus, oh no, it's plus 8 over 5 e to the negative 2t, and then we have plus 3 times x. So this is going to be what? We're going to have 3 times x, so 12 over 5 e to the 3t minus 12 over 5 e to the negative 2t. Okay, so let's simplify this. So let's see, we have 12 plus 12 is 24, but then divided by 2 gives us 12 over 5 e to the 3t. And then we have 8 minus 12 is minus 4. And then divided by 2, it's going to be 2 over 5. Okay, so there's our two solutions. So let's put a box around them. So there's y of t, and here is x of t. Okay, great. And I guess another way that we could write this as well is we can sort of combine them into like a vector form. So we could do the following. So maybe let me just end this example here, and then I'll just make a note here. So note what we have is if we put it in like a vector form, so x of t, y of t here, then we're going to get the following. So let me just write it out in full, and then we'll split it up. So we have this, and we have this. Okay. So the way vectors work is I can actually split this into like 2 vectors here like that. And then because I have the same thing on both sides here, I can factor it out. So let me do that. So I'll end up getting 4 over 5, 12 over 5 times e to the 3t. And then I'll have, maybe I'll keep it as a plus, negative 4 over 5 and negative 2 over 5, and then e to the negative 2t. And let me just think here. I might want to kind of factor out like another constant here that's sort of in common. So 4 divides out here, so I can divide this out by 4 over 5, and I get 1 and 3. And then here I'm going to divide out by the 2 over 5, and that gives me the vector 2 and 1. Okay, so now I want to show you something kind of cool, giving you a bit of a preview of where linear algebra shows up here. So this is our another way to write our solution in a vector form. So let me just point out some interesting things here. So first of all, we have this 3 and minus 2 here. So those are going to be important. And then I'm going to highlight also this vector here, this 1 over 3, or sorry, 1, 3 vector, and this 2, 1 vector. Okay. So the original system of differential equations, we can actually write it as the following. Maybe let me just get rid of this of t part. So the original system of differential equations, if you recall, it was given by, let's see, which number am I doing here? Well, maybe I'll just copy it. I don't, oh yeah, I'm doing number 3. Okay, so let's just copy that and bring this down here. Let's see, so I want to make this blue. Okay. So again, this is like writing the differential equations in vector form. But this matrix here, we can write this this vector here as a matrix times a vector. So the way matrix vector multiplication works, we write the coefficients of the variables here, and then when we multiply by this vector x, y, then we get this. So when you multiply a matrix times a vector, we're going to take this vector here, and on each row, we're going to do -3 times x plus 2 times y, and that's what we get here. And then the second row is -3 times x plus 4 times y. So that's matrix vector multiplication. Okay, so this matrix here is really the key to understanding this system of differential equations. So let's have a look at this matrix here. And I want to show you something very interesting that's happening with this matrix and these 2 vectors here and these 2 values here. So it turns out that this vector is what's called an eigenvector of this matrix, and the corresponding eigenvalue is this 3. And this vector here is an eigenvector of this matrix, and the corresponding eigenvalue is -2. So what does that mean? So now, so then let's check this out. So we'll take this matrix, copy that, put it right here. We'll take this first, what I called an eigenvector, paste that there, and let's do the multiplication here. So just like we had here with the x and the y, we're going to do -3 times 1 plus 2 times 3. So negative 3 times 1 plus 2 times 3. So that's how we calculate that. Negative 3 times 1 plus 2 times 3. And on the bottom, we have negative 3 times 1 plus 4 times 3. Okay, so again, that's negative 3 times this 1 plus 4 times this 3. Okay, and what do we get over here when we compute this? We get negative 3 plus 6, that's going to be 3. And on the bottom, we have negative 3 plus 12, which is 9. And now notice something very interesting happening here. So this vector started as 1, 3. We multiply by this matrix and we get 3, 9, which is precisely 3 times the original vector. So this is actually equal to 3 times this vector. And what is this? What is this 3? That is called the eigenvalue, and that is exactly what is showing up right there. Pretty amazing. So let's highlight that 3. So, and let me label this. So therefore, this is an eigenvector of the matrix and this 3, oops, and 3 is the corresponding eigenvalue. Okay, and this is really nice because this would give us like another way to solve this differential equation, this system of differential equations. If we could just take this matrix and compute its eigenvalues and eigenvectors, which is it's a pretty easy thing to do. We could immediately go from the eigenvalue, eigenvectors of this and immediately write down the solution. Now, of course, we would need to determine these values here. That comes from the initial conditions. But that's the idea. And so let's just check again. If we multiply this matrix times this vector, we should get -2 times this vector. So let's see if that works out. So let's do that. So let's take this matrix, put it there, take the other eigenvector, put that there. Let's do the multiplication. -3 times 2 plus 2 times 1 minus 3 times 2 plus 4 times 1. Okay, so again, -3 times 2 plus 2 times 1, that's the first row. And then -3 times 2 plus 4 times 1, and that's the second row. So that's how you do matrix vector multiplication. And we get -6 plus 2, -4. And -6 plus 4 is -2. And what is that? That is exactly -2 times this vector. And that means that this vector is an eigenvector, and the corresponding eigenvalue is -2. So therefore, this and this number are an eigenvector slash eigenvalue pair of the matrix like that. So when you take linear algebra, you're going to learn how easy it is to calculate eigenvalues and eigenvectors for a matrix like this. You can also just go into any kind of numerical linear algebra software, where a lot of mathematical software actually has the ability to compute eigenvalues and eigenvectors of a matrix. So you literally just put in this 2x2 matrix, you say, give me the eigenvalues and eigenvectors, and you're done. You're done. You have the final solution right here. So that would immediately give you this final solution, except you still need to calculate, this 4/5 and -2/5, which come from the initial values. Okay, so just giving you a bit of a preview. This is not required for solving this type of problem on the exam. For the exam, I recommend that you just do this method of elimination. So where you solve one equation for the first equation for y, or the second equation for x, and then substitute into the other equation. And let me erase this stuff here, because this was clearly not the best way to calculate that value. So I'm just going to erase that. Okay. So it's the method of elimination. It's just essentially eliminating the, we're basically taking this second equation and we're eliminating the y terms. So that's why it's called the method of elimination. So we're eliminating these y terms and we just get x terms. Okay, so let's do another example. Okay, so again here, if you wanted, you could actually compute the eigenvalues and eigenvectors for this matrix. This turns out to be a little bit more complicated than the first example, because the eigenvalues and eigenvectors of this matrix are complex numbers. And we'll actually see that when we solve this, we're going to get cosine and sine terms, which come from complex or imaginary square roots, imaginary roots of the characteristic polynomial. But let's just use the method of elimination to solve this, because it's pretty straightforward. Okay, so I'm just looking at this. I want to either solve this equation for y or solve this equation for x. Let's do something different. So let's instead of solving the first equation for x, for y, we'll solve the second equation for x. And what do we get? So we're going to get x is equal to 1/2 y prime minus y. And then we will need the derivative. So we'll take the derivative. We get this. And then we'll substitute into equation 1, or into the first equation. Let me say it that way. Into the first equation. Okay, so the first equation is this. Okay, and we need x prime, so it goes right there. And that's going to be equal to negative 3x minus 4 times this guy. Copy. Let me just get rid of that and just put a dot. Okay. Oh, did I didn't do the right thing, did I? Okay, that was a mistake. I wanted to substitute the x, right? So not the y. So let me put that over there. So this will go right there. Bring the dot over, and then we have minus 4y. Okay, that's better. Right, so once you do the substitution, it should all just be, it's all x or all y. So we've eliminated one of the variables. And now we just need to simplify this differential equation. I'll multiply both sides by 2 negative 3y prime plus 3y. Almost made a mistake there. And then minus, I'm multiplying by 2, right? So 8y. Okay. All right. So y double prime, let's see, I bring the 3y prime over. So that'll be plus 2y prime. And then minus 5y. So that'll be plus 5y is equal to 0. So there we have it. A nice homogeneous differential equation. Like that. Okay. So let's solve this. So again, let's use so in this case, we actually don't have a initial conditions. So, so we're just looking for the general solution. So let's see. So y, let's see, what am I doing? So I want the characteristic equation. So r squared plus 2r plus 5 is equal to 0. And then we get, let's see, I'm going to complete the squares here. So I get r plus 1 squared plus 4 equals 0. And then I know that the roots are going to be negative 1 plus or minus 2i. Okay. And so therefore, the solution is y of t is equal to e to the negative t times c1 cosine 2t plus c2 sine 2t, like that. And so that's the solution for y. Okay, and now we want to figure out what is the solution for x. So x x is equal to this right here. So that's x. So we'll copy that. Okay, so since x is equal to this, we have, let's see, is there a way to, like, do we know what y prime is? Is there an easy way to get y prime, or do we just have to differentiate? So yeah, I don't think we know what y prime is. Let's see, is there a y prime here that I could grab? I don't think so. So I think we're just going to have to do the differentiation. So let's do it. So y prime is equal to the derivative of the first term times the second plus the first times the derivative of the second. Okay, so there's the derivative, and now we can put that all together. So since x is equal to that, we have x of t is equal to 1/2 times y prime. So this guy, maybe I should simplify that first. Let's see, I'm going to have negative c1 minus 2c2 c1. Oh, no. I almost made a mistake. So it's the cosine is here and here. So it'll be negative c1 plus 2c2. And then this will be negative c2 minus 2c1. Let me put the c1 first. So minus 2c1 minus c2. And let's see if I can just get this all to fit into a single line. And then I get, this would be sine 2t. Okay, that looks okay. Now I'm going to take that expression and I'm going to put it in here. So, and it doesn't quite fit. Oops, it doesn't quite fit. So I'll just make it a little bit smaller. Okay, so that's the y prime, and then minus y, and that is simply this. And okay, so therefore x of t is going to be what? So again, I can factor out this e to the negative t here and here, and then sort of simplify everything. So let me see what I'm going to get here. So this is, so on the inside I'm going to have this minus this. So that's going to be a minus 2c1 plus 2c2. Yeah, okay, so let's write that out. I'm trying to do maybe too much in my head. So let me factor out the e to the negative t first. And then this first term is going to be negative 2c1 plus 2c2 cosine 2t. And then here we have this and then minus this. So I'm going to get minus 2c1 minus 2c2. Okay. Okay. And is there any way I can get that term to fit? I guess I could just squish it. So let me write, let me just grab this. So sine 2t. And now what's nice about this is the this 1/2 here will cancel these 2's in here. So that'll be nice. So let's do that. So I get e to the negative t times negative C1 plus C2 cosine 2t plus negative C1 minus C2 sine 2t. Okay, and there's the final answer. Now, if we had done the solution in the other direction, then if we had, solved for x of t first and then figured out what y of t is, then we're going to get a solution that looks different than this. So we're going to get, let me just make these square brackets. So it looks a little bit nicer, I think. So we'll get a different looking answer, but it'll be equivalent to this one. So if we did x of t first, then we would have had c1 cosine 2t plus c2 sine 2t. And then up here for the y term, we would get something else here, which will involve c1 and c2 here, and something that would involve c1 and c2 here as well. So that's what would happen. Okay, so I think that's it, and we could check the answer in the back for this. So number 5 to see which one they ended up getting in the back. So yeah, they solve for x first, and then they solve for y, and they got a different answer in the back, but it'll be equivalent to this one, to the one that we have. Okay, so that is basically the end. So on the exam, you would just stop there. Now, I don't know if this would be so interesting, but we could try it to see what happens. So we could write this solution out in vector form. So what is the value of, let's grab this one first. So that's the y term, and then this is the x term here. Like that. Okay, so it's just kind of some bonus material here. Now, I guess what we could do is combine these in maybe a couple of different ways. I mean, we could put all the C1 terms together, and then the C2 terms, or I guess we could put the cosine terms together and then the sine terms. Yeah, I don't know if that would be completely worth it, but let's just see. Let's just see. So we're going to get x of t, y of t, and then we'll have negative c1 plus c2 times c1, and then the exponential of minus t times cosine 2t. And then we also have plus negative c1 minus c2, and then c2 down here. Okay. So yeah, I don't know if this would be so to really like make the connection between this and like the eigenvalues and eigenvectors of the original matrix. you do sort of have to involve a complex or imaginary number somewhere, and then combine them. And then you can kind of notice that these terms that are appearing here are coming from the eigenvalues, which actually, so the eigenvalues of that matrix will be precisely these guys. So those are the eigenvalues of the matrix. And then you would have to figure out what the eigenvectors are. And the eigenvectors will also involve imaginary numbers. And so you would then take those eigenvectors, and that would give you somehow these expressions here. Anyway, so there's more details. If you're interested in some of this material, you'll probably see it in the future at some point. But also in the book, they go over this in later on in chapter 5 to sort of see how to get this solution directly from eigenvalues and eigenvectors. Okay, so let's move this guy up here. So let's do one more problem. And I think, so this one doesn't have any initial conditions, but you can see it's this non-homogeneous, which, yeah, let's just do this kind of the standard way. So I wanted to mention that there are ways that you could use Laplace transforms to directly solve a problem like this. And maybe what we could do is revisit the first problem that we did here. We could revisit this because this one actually has initial conditions. We could revisit this and see how we could solve this using Laplace transforms. So let's try that at the end, in case you're interested in that method for solving these. But let's go ahead and just do this kind of the standard way. So we could either solve this first equation here for y, or we could solve the second equation here for x. So let's go back and solve this first equation here for y. That actually looks quite easy because y is just there. We just move everything over to one side. So let's solve the first equation for y. So we're going to get y is equal to x prime minus 4x minus 2t. I think that is okay. Yes. And then we take the derivative of it. The derivative of 2t is 2. And then we substitute into the second equation. The second equation. So the second equation is this one. So we're going to substitute into this equation here. So the first thing on the left-hand side, we have this. And then on the right, make sure I do it the correct way this time, the y is equal to this guy. Okay, and now let's rearrange everything, put all the x's on one side, and we have x double prime minus 5x prime. And then we have, on the left, we have minus 6x, so move it to the right, so plus 6x, and then move this 2 to the left, or to the right, move this minus 2 to the right, and we get 2 minus 2t. Okay, so there is our differential equation. And in order to solve this, so first we need to find the complementary solution, so which is the general solution for the homogeneous problem. And then we need to find a particular solution using the method of undetermined coefficients. So let's do that. So here we have r squared minus 5r plus 6 equals 0. There's the characteristic equation, and we factor it. We get r minus 2 times r minus 3. And so then r is equal to 2 comma 3. And that gives us our complementary solution, which is c1 e to the 2t plus c2 e to the 3t. So there's our complementary solution. And now we need to find a particular solution. And in order to do that, we need to use the method of undetermined coefficients. So we need to take this right-hand side and look at all the terms that are appearing in this this function and in all of its derivatives as well. So the function is f of t is equal to 2 minus 2t. And if I take the derivative of that, then I'm going to get negative 2. And now I can pretty much see that all the terms that are appearing here that we need are going to be 1 and then t. So here we have 2 times 1. So 2 times 1 here, and then this is negative 2 times t. So we get the 1 and the t. And then here we just have negative 2 times 1, and so that's the 1 there. So we already have that. So there's our functions that we want. And so now the particular solution we know is going to have the form a times phi 1 plus b times phi 2. And that is equal to a times 1. So I'll just write a plus b times t. So now what do? We just take this equation and we substitute it into our differential equation here. So we're going to need, so xp is equal to a plus bt. Let's erase that. The derivative is equal to b, and then the second derivative is equal to 0. So now we'll substitute this stuff into our differential equation, which is this one. Okay, so we're going to put the particular solution in here, and then we'll figure out what the a and the b should be. So we get 0 minus 5 times b plus 6 times a plus bt, and that's equal to 2 minus 2t. And so we end up getting 6a plus b, sorry, 6a, so 6a minus 5b plus 6bt is equal to 2 minus 2t. So we can match up the coefficients. So this term here is equal to that. And then the other term here is equal to this minus 2. So therefore, we have 6a minus 5b is equal to 2, and we have 6b is equal to minus 2. So now we can solve for b. It's going to be minus 1/3, and then we can use that over here. So we get 6a minus 5 times negative 1/3 is equal to 2. So 6a plus 5/3 is equal to 2. Maybe I'll just move that over right away. So it's going to be 2 minus 5 over 3. This is going to be 6 minus 5 over 3. 6 minus 5 over 3. So that'd be 1 over 3. Yeah, 1 over 3. So 1/3. So it'll be 1/3 divided by 6. So we're going to get 1 over 18. Okay, so there's our coefficients that we needed. And so therefore, the particular solution is going to be 1 over 18 minus 1/3 times t. There's our particular solution. And so therefore, the general solution for x of t is the complementary solution, this guy. There's our complementary solution. Plus our particular solution. Okay, so that is x of t right there. And now we need to calculate y of t. So y of t is given to us by this expression here. So y of t is going to be given here. So just put that down here. That's what we're going to use. So we're going to say since y is equal to this, we have the following. Okay, but in order to use that, we need x prime. So let's compute x prime. So x prime is going to be 2c1 e to the 2t plus 3c2 e to the 3t plus, or in fact, it's minus 1/3. Okay, so we'll have y of t is equal to x prime. Okay, and then we have minus 4 times x. Right there. Let me just remove these parentheses. And then we have minus 2t. Okay, let's simplify this. So let's see. We have 2c1 minus 4c1. So that is going to be minus 2c1 e to the 2t. And then we have 3c2 minus 4c2. So that will be minus c2 e to the 3t. And then we have minus 1/3 minus 4 times 1 over 18. Okay, let me calculate that over here. Minus 4 over 18, that'll give us minus 2 over 9. So it'll be minus 3 minus 2 over 9 is minus 5 over 9. Okay, so that'll be minus 5 over 9 for that term. And then we're going to have minus 4 times negative 1/3 t, and then minus 2t. So we're going to have 4 over 3 minus 2, so that's 4 over 4 minus 6 over 3, which is negative 2/3. So we'll have negative 2/3 times t. Yes, yes, good. Okay, and that's it. That's our final answer right there. Because we don't have any initial conditions, so we're just going to stop right there. And we can check if this is the answer in the back for this problem number 7. Okay, so they're using A1 and A2 instead of C1 and C2, but otherwise it's exactly that for x of t. And then for y of t, it is exactly that as well, except I'm having trouble seeing because the lights, it is getting dark in here. So let me turn on some lights. So let me check that again. So negative 2/3 t minus 5/9. Yeah, okay, so that is matching. Perfect. Okay, so one more thing I wanted to do was let's just see if we can, if you really like Laplace transforms, let's see if we can just use Laplace transforms to do this. Now, even without initial conditions, there's no reason why we couldn't use Laplace transforms as well. So let's go back and visit this example. So you could use Laplace transforms even without initial conditions. You just have to say, you know, x of 0 is x naught and y of 0 is y naught, and then just plug that in. So that's entirely possible. But let's look at this example again using Laplace transforms. Using Laplace transforms, we have s, maybe I won't use the square bracket, so it'll be s x of s minus x of 0 is equal to negative 3x of s plus 2y of s. And we have s y of s minus y of 0 is equal to negative 3x of s plus 4y of s. Okay, now what's going to happen here? So let's move all the Laplace transforms to the left, and we'll move these guys over to the right here. So all this stuff here, I'm going to put it over here. So I'm going to have s plus 3x of s minus 2y of s. And that's equal to x of 0. X of 0 is 0. And then we have s minus 4 y of s. Oh, let me put the y of s on the other side here. Put that over here. Let's see, just kind of make it line up here a little bit. And then the x term will be 3x of s, like that. And then this y is going over here, and that is equal to 2. So we'll put a 2 there. All right. So this looks really nice. Let's put a nice box around it, if I can. So what do we have here? This is actually a linear system. It's a linear system in terms of x of s and y of s. So we can use Cramer's rule to solve for x of s and y of s. So using Cramer's rule, x of s is going to be what? So on the bottom, the matrix is 3 plus s and then minus 2, and then 3 and s minus 4. Okay. All right. I'm just kind of thinking about the matrix that we have here as well. Anyway. Yeah, looks kind of similar to that matrix we have. This expression here, actually, you could think of it as this will be S0, 0, S minus 3, 2, minus 3, 4. So actually, that's what's appearing right there. So you have S minus 3, so it's S plus 3, 0 minus 2, so you get minus 2, 0 minus 3, so it gives you 3, and then S minus 4, and that gives you S minus 4. And it turns out this is precisely the expression that you would be using in order to determine the eigenvalues of this matrix. So yeah, so it kind of looks like this: S times identity minus the matrix. So that's what this ends up looking like. And we're taking the determinant of that, and that's precisely what you do to find eigenvalues. So just to let you know that this expression down here is precisely the thing that you would be calculating to determine eigenvalues of a matrix. Okay. So it's really neat how all this stuff sort of connects together. So on the bottom here, this determinant is s plus 3 times s minus 4, and then minus 3 times minus 2, minus 6, so plus 6. Okay, so we're going to have to, that's what's in the bottom. In the top, what do we have? Oh, I need to move this down a little bit to avoid that page break. So in the top, we're going to replace the first column here with the right-hand side, 0, 2. So in the top, we're going to have 0 minus minus 4, so plus 4. Okay. And therefore, x of s is equal to 4 over s squared. Let's see. That'll be 3 minus 4 is minus 1, so minus s, and then plus, or minus 12. So minus 12 and then plus 6. So minus 12 plus 6 is minus 6. And then we can factor that as s minus 3, s plus 2. Okay. And that actually gives us our eigenvalues of the matrix. So the eigenvalues are going to be 3 and minus 2. So that's normally what you would do to compute eigenvalues, is you form this, take the determinant, and then figure out what the roots are. And so you get 3 and minus 2. Those are the eigenvalues of that matrix. Okay, so now let's do partial fractions here. So that's what we'll do. And then, so let's do this first, and then we'll come back and figure out what y is. So y is just the second part of Cramer's rule, y of s. Okay, so let's do this first. So we get A s plus 2 plus b s minus 3, and then s equals minus, let's do 3 first. So s equals 3 gives us 5a, so a is 4 over 5. Oh, that's that 4 over 5 that we had when we solved this problem the first time. And then s equals minus 2, and we get 4 is equal to minus 5b. So b is minus 4 over 5. Okay, so therefore, x of s is equal to 4 over 5 times 1 over s minus 3 minus 4 over 5 times 1 over s plus 2. Yep. And so therefore, x of t is 4/5 e to the 3t minus 4/5 e to the negative 2t. And there we go. Does that match what we had before? I'm just going to zoom over here, and let's have a look right here. X of t is 4/5 e to the 3t minus 4/5 e to the negative 2t. So that is a match. That is a match. Okay, so that's exactly what we have here. So that's perfect. Okay, so now let's do the y of s. So y of s is the second part of Cramer's rule. So we'll copy this and paste that there. So now we're doing y of s. And in this case, we are going to put this right-hand side over here. And then in the second column, and then in the first column, it's going to be this. Okay. And we've already computed this denominator and factored it. So this denominator is equal to this, and then we multiplied that out and we factored it. So we already know that this thing here is equal to this. So that's what I'm going to put down there. So copy that, put that right there. And then the numerator is going to be s plus 3 times 2 minus 0. So we get 2s plus 6 in the top. And we're going to do partial fractions here. Like that. Okay, so we get 2s plus 6 is equal to a times s plus 2 plus b times s minus 3. And then s equals 3. This gives us 12 is equal to 6 times, oh no, 5 times, I almost made a mistake. 5 times a. So a is 5 divided by 12. And then s equals minus 2. On the left, we get 2. And on the right, we have minus 5b. So b is equal to minus 5. Oops, I almost made a mistake. Is equal to minus 2 divided by 5. Oh, and I see I made a mistake up here, actually. 12 divided by 5. Okay, so therefore, y of t is equal to 12. Oh, maybe I should summarize the. So we get y of s is equal to 12 fifths times 1 over s minus 3 minus 2 fifths times 1 over s plus 2. Yeah. And so therefore, y of t is equal to 12 fifths times e to the 3t minus 2 fifths e to the negative 2t. All right. So that's it. If you prefer to use Laplace transforms, and let me just check to see that that is the same. So I'm just looking at my thumbnails here. 12 over 5 e to the 3t. Yep. Minus 2 fifths e to the negative 2t. Yes. So there you have it. If you like to use Laplace transforms to solve a system of differential equations like this, so you don't have to use the method of elimination. You can use Laplace transforms, and in that case, when you use Laplace transforms, you'll end up getting a linear system like this for x of s and y of s, and then you just use Cramer's rule like we've been doing many times in this course to solve the linear system very easily. And then you just use partial fractions to find the inverse Laplace transform, and you do the same for y. So Cramer's rule, partial fractions to find the inverse Laplace transform, and you're done. So different ways to do this. And also, you know, as I sort of mentioned, there's all this like really interesting linear algebra way to do this as well, by writing down the matrix for that system of differential equations, computing its eigenvalues and eigenvectors, and then you just immediately get the solution like this. Yeah, so you can just immediately, compute the eigenvalues, eigenvectors, 3 and minus 2, get the eigenvectors 1, 3, and 2, 1, which I didn't explain how to do that, but it's a standard thing that you learn in the linear algebra class. And then after that, use the initial conditions to determine these numbers here. So, but I think this the way we did it here with Laplace transforms, it was really cool. I like this a lot. So my preference would be to use Laplace transforms to do this type of question rather than using the elimination technique, which is the main topic of this section is the method of elimination. But I like Laplace transforms. Very cool way to do it. And my understanding is that this is kind of like the way the engineers like to do this stuff as well, is using Laplace transforms. So that's it. That's the last lecture in this class. So do have some practice with solving these types of problems using elimination or Laplace transforms, and expect a question like this on the final exam. And that's it. So thanks so much for watching all these lectures, and I wish you all the best in final exams and in your adventures with differential equations in your courses in the future and in your career. So thanks so much, and goodbye.